Bertha was not supposed to stop. This was a tunnelling machine wider than a 5-story building, a 57.5-foot steel giant built to chew through the ground beneath downtown Seattle. Its job was simple in theory: dig a new highway tunnel under the city while life continued above it. Then, after just over 1,000 feet, everything froze. Deep underground, the cutterhead stopped turning. The machine was sealed inside the very tunnel it had already built 1,000 feet from the launch pit, with soil, groundwater and city streets pressing in around it. There was no crane big enough waiting above. There was no way to just tow it backward. So the question became brutally simple. How do you repair one of the biggest tunnelling machines on Earth when the broken part is buried beneath Seattle? This was no longer just a construction problem. It was a rescue mission. Seattle's problem started above ground, with a highway that had been built for a different city. The Alaskan Way Viaduct was a double-deck concrete freeway running along the downtown waterfront. Since the 1950s, it had carried State Route 99 past offices, piers, ferries and stadium traffic. For commuters, it was one of the fastest north-south routes through Seattle. For the waterfront, it was a wall of concrete, noise and shadow. Just listen to what the city lived beside every day. Then in 2001, the Nisqually earthquake shook western Washington. The viaduct did not collapse, but inspections found serious damage. Columns cracked, joints shifted. The structure had survived, but it had also revealed the problem engineers feared most. Another major quake could bring it down. That made the viaduct more than an eyesore. It was a major transportation route sitting above streets, sidewalks and businesses in a region where earthquakes were not hypothetical. Keeping it open meant accepting risk. Closing it without a replacement meant pushing tens of thousands of vehicles into already crowded downtown streets. Seattle needed a new plan, and the chosen answer was enormous. Replace the viaduct with a 9,270-foot tunnel carrying State Route 99 beneath the waterfront corridor. The tunnel promised several things at once. It would keep regional traffic moving through the city. It would remove a vulnerable elevated freeway from the waterfront. It would open land for parks, views and redevelopment. And it would let Seattle rebuild one of its most valuable public spaces without leaving a highway overhead. But there was a catch. Digging a highway trench through downtown Seattle from the surface would have meant tearing through streets, utilities, businesses and daily city life. So the project made its boldest choice. Instead of opening the city from above, Seattle would go underneath it, using one of the largest tunnel boring machines ever built. Its name was Bertha. Bertha was not a machine Seattle could simply buy off a shelf. It was custom built for this job by Hitachi Zosen in Osaka, Japan, then shipped across the Pacific in massive pieces and assembled in Seattle in 2013. By the time it was ready, it was among the largest tunnel boring machines ever made. The numbers were almost difficult to picture. Bertha was about 326 feet long, roughly the length of a downtown office tower laid on its side. Its cutterhead was 57.5 feet across, wide enough to carve a tunnel that could eventually hold a double-deck highway. Altogether, the machine weighed thousands of tons, with a rotating front face, conveyor systems, hydraulic jacks, motors, seals, pipes, controls, and steel structures, all packed into one moving underground factory. At the front was the cutterhead, a circular wall of steel fitted with cutting tools. As it turned, it chewed into the ground. Behind it, crews worked inside pressurized sections, removed excavated soil, installed concrete tunnel rings, extended utilities and kept the machine moving forward a few feet at a time. Bertha was named after Bertha Knight Landis, who became Seattle's first female mayor in the 1920s and the first woman to serve as mayor of a major United States city. For a project meant to reshape Seattle's waterfront, the name gave the machine a local identity. This was not just equipment, it was a civic symbol, painted, photographed and followed by a city waiting for the viaduct to come down. But the size that made Bertha impressive also made it unforgiving. A machine like this cannot easily be pulled backward. It cannot be lifted out when something goes wrong. Once launched, it is expected to keep advancing through soil, groundwater, old fill, and whatever else lies beneath the city. From the surface, Bertha looked like a triumph of engineering, a purpose-built machine assembled for one of Seattle's most ambitious infrastructure projects. Underground, that same scale would soon create a much darker problem. If Bertha failed deep below the waterfront, it would become almost unreachable. To understand why Bertha's failure mattered, you have to understand how the machine was supposed to move. At the front, the cutterhead did the eating. This huge steel disc rotated against the face of the tunnel, scraping and crushing whatever Seattle placed in its path. Glacial clay, sand, gravel, old fill, mud, groundwater, and buried debris from earlier generations of construction. The cutting tools did not slice through the ground like a kitchen knife. They broke it apart under pressure, turning a solid wall of earth into loose material that could be carried away. Behind that spinning face was a pressurized chamber. Its job was to keep the ground and water from rushing into the tunnel while the cutterhead worked. The excavated material collected there then passed into a screw conveyor which controlled how quickly spoil left the chamber. That mattered because removing too much material too fast could let the ground settle above. Removing too little could choke the machine. From there, the dirt entered Bertha's trailing factory. Conveyor belts carried the spoil backward through the machine and out toward the surface. At the same time, cables, pipes, pumps, ventilation ducts, hydraulic systems, and control rooms kept the operation alive. Crews were not just driving a drill, they were working inside a moving industrial plant deep under a city, while the front of it ground forward through unstable material. The tunnel was not left as raw dirt after Bertha passed. Just behind the cutterhead, the machine built the finished structure one ring at a time. Curved concrete segments were lifted into position by a rotating erector arm. Piece by piece, they formed a complete circular ring, like sections of an enormous concrete barrel. Once locked together, those rings became the permanent tunnel lining. Then the same finished ring became part of the machine's engine. Hydraulic jacks pressed against the concrete Bertha had just installed. As the jacks extended, they shoved the cutterhead into fresh ground. After a short advance, the jacks retracted. Another set of concrete segments went in, and the process repeated. That was the genius of a tunnel boring machine. It did not simply dig a hole and then build a tunnel later. It excavated, removed spoil, installed the lining, and pushed itself forward as one continuous sequence. Every few feet of movement depended on the last few feet of tunnel being strong enough to push against. So when Bertha was working properly, the city above saw almost nothing. Underground, the machine was chewing, hauling, building, and crawling all at once. On July 30th, 2013, Bertha began boring beneath Seattle. At the launch site near the waterfront, the mood was confident. The machine had been built for this exact job: drive a highway tunnel under downtown, replace the aging Alaskan Way viaduct, and do it without tearing open city streets block by block. Officials posed for cameras. Reporters covered the start like a milestone. After years of planning, the world's largest tunnel boring machine was finally moving. Progress underground was never going to look fast. Bertha advanced in short pushes, not long sprints. The cutterhead chewed forward. Spoil moved back through the machine, and the crew installed another concrete ring behind it. Then the hydraulic jacks pushed off that ring, and the cycle started again. Foot by foot, the tunnel grew. Each ring marked another small section of permanent structure. Above ground, traffic kept moving, office towers stayed open, and most people experienced the project as construction fencing, truck routes, and occasional updates. The real work was happening far below, where Bertha was slowly drawing a new road beneath the city. By December, the machine had travelled roughly 1,083 feet. That was an enormous distance for a machine crawling through wet, mixed ground under Seattle. But it was still only a fraction of the planned tunnel. Bertha had many thousands of feet left to go. Then, on December 6th, 2013, the steady rhythm broke. The machine stopped. At first, there was no clear public answer for why. Crews knew something was wrong at the front of the machine, but from the surface, the problem was hidden under layers of soil, groundwater, steel, and concrete. Bertha had made it through the first 1,000 feet. Now it would not move. The problem was not just that Bertha had stopped. The problem was where it had stopped. This was not a machine sitting in a repair bay with cranes, open floor space, and mechanics walking around the outside. Bertha was buried beneath Seattle, roughly 1,000 feet into its drive, inside a tunnel only slightly wider than the machine itself. Its most important working parts were at the very front, pressed against soil and groundwater, with the city above and the unfinished tunnel behind it. That changed every repair decision. If a bearing failed in a factory, crews could expose it. If a motor burned out in a workshop, they could remove panels, bring in heavy lifting gear and replace the part. Underground, access was narrow, slow and dangerous. The cutterhead was not sitting in the open. It was sealed behind the face of the tunnel, exactly where the ground pressure and water pressure were highest. The first question was simple and also impossible to answer quickly. What had Bertha hit? Crews had to sort through several possibilities. The cutterhead might have struck an object left in the ground. The soil ahead might have changed in a way that overloaded the machine. Or the machine itself might have suffered a mechanical failure deep in its drive system. Each possibility led to a different fix, and each fix carried a different risk. Meanwhile, the project could not simply wait without consequences. The tunnel was supposed to replace a vulnerable elevated highway along Seattle's waterfront. The route ahead was still mostly unbuilt. Every idle day threatened the schedule, pushed costs higher, and fed public doubt about whether the mega project had been too ambitious from the start. Above ground, officials and contractors faced questions they could not yet answer with confidence. Below ground, crews were dealing with a machine too large to pull backward, too buried to inspect easily, and too essential to abandon. Then one early theory began to take shape. Before Bertha stopped, sensors and crew reports suggested the cutterhead may have encountered something unexpected in its path. Not a change in paperwork, not a routine pocket of soil, a physical object in the ground. And if that was true, the breakdown had begun with a collision. Investigators soon found a very real object in Bertha's path, a steel pipe left over from an old groundwater monitoring well. It had been installed years earlier during planning for the tunnel, then abandoned below the surface. On paper, it was supposed to have been removed or dealt with before the machine arrived. Instead, a section of it remained in the ground, directly in the zone Bertha was cutting through. For a while, that pipe looked like the obvious culprit. It was exactly the kind of thing a tunneling machine did not want to meet unexpectedly. Bertha's cutterhead was built to chew through soil, gravel and mixed ground, not to casually swallow a loose steel obstruction that could jam tools, damage openings or send abnormal loads through the front of the machine. But as crews dug deeper into the evidence, the story became less simple. The pipe may have been struck. It may have contributed to the trouble, but it did not fully explain why Bertha overheated, lost performance and suffered damage in one of its most critical systems. The real problem was not just what the cutterhead hit, it was what happened behind the cutterhead inside the main bearing and seal system that allowed the entire front of the machine to rotate. That main bearing was one of Bertha's most important components. It carried the enormous cutterhead and let it turn under massive loads while the machine pushed forward. To protect it, engineers relied on seals designed to keep groundwater, soil and grit away from the bearing's lubricated interior. Those seals were supposed to separate two worlds, the dirty, pressurized ground at the tunnel face and the controlled mechanical space inside the machine. Once that barrier was compromised, the system became vulnerable. Water and debris appear to have made their way past the seal arrangement. Contamination reached areas where clean lubrication and controlled temperatures were essential. Friction increased, heat built up, components around the bearing system began to deteriorate. That explained why the stoppage was so serious. This was not only a dented tool or a broken scraper on the cutterhead, the damage was tied to the machinery that made the cutterhead spin at all. If the bearing system could not be protected and cooled properly, Bertha could not safely continue mining. And the most frightening part was its location. The failed seals and damaged bearing components were not sitting in the service area behind the machine. They were at the front, buried against the earth on the far side of a massive steel machine that could not simply be opened like a garage door. By this point, Bertha was not a machine sitting in a garage. It was a 1,000-foot-long underground factory, assembled in place as it moved. At the front was the cutterhead, pressed into wet, unstable soil. Behind it were the main bearing, motors, screw conveyors, hydraulic systems, electrical rooms, control areas, and a long train of support equipment. Behind all of that was the tunnel Bertha had already built, lined with concrete segments as the machine advanced. That tunnel lining was not just scenery, it was part of the whole mining system. Bertha pushed against the finished rings to shove itself forward, while new rings were installed behind the shield. The machine, the lining, and the backup gear were all working as one connected process. Had a brutal answer. There was nowhere practical for it to go. Bertha was not designed to reverse through the completed tunnel like a train. Its largest parts were too wide, too heavy, and too deeply integrated with the equipment behind them. Even if crews tried to dismantle it underground, the pieces that mattered most were at the very front, beyond the finished lining, buried in pressurized ground. That front section was the dangerous zone. The cutterhead and bearing area was sitting ahead of the completed tunnel, surrounded by soil and groundwater that wanted to push in. Opening that area from inside the tunnel risked losing ground, flooding the workspace, or creating movement at the surface above. And this was downtown Seattle. The ground above Bertha was not an empty field. It held streets, utilities, buildings, and the elevated highway the tunnel was meant to replace. Any repair plan had to protect the city as much as the machine. Conventional recovery had run out of room. Crews could not simply pull Bertha backward, and they could not safely reach the damaged components from inside the tunnel. To fix the machine, engineers would have to attack the problem from the outside. They would have to dig down from the surface and build a rescue shaft around Bertha's buried front end. The rescue plan was to build a new hole in the city directly in front of Bertha. Not a small inspection pit, a massive vertical access shaft, roughly 120 feet deep, wide enough for crews, cranes, tools, and eventually pieces of the tunnel boring machine itself. It had to reach the buried cutterhead from above without letting the surrounding ground collapse into the excavation. The location made the job unusually tense. Crews were working in downtown Seattle, near active streets, buried utilities, nearby buildings, groundwater, and the tunnel Bertha had already completed. The shaft could not shift the soil in a way that damaged pipes or pavement. It could not drain the ground so aggressively that nearby structures settled, and it could not destabilize the stalled machine sitting beside it. So before they could dig, they had to create a controlled box in the ground. Engineers strengthened the soil around the future shaft, then installed deep retaining walls to hold back earth and water. The goal was to turn a section of unstable urban ground into something that could be excavated like a giant construction chamber. This was the rescue operation at street level. Once the walls were in place, excavation began in stages. Crews removed soil from inside the shaft, working downward while braces and support systems held the walls apart. Pumps dealt with groundwater. Survey teams watched for movement. Every level brought them closer to the front of a machine that was never meant to be uncovered from above. And the deeper the shaft went, the stranger the scene became. A modern tunnelling machine was being reached the way miners might reach a trapped object underground. Dig beside it, stabilize everything around it, then open just enough space to work. At the bottom, crews needed to expose Bertha's cutterhead and the front shield area. That did not mean simply scraping away dirt until the machine appeared. They had to manage pressure, water, and ground conditions around the face, because the cutterhead was still sitting in the same soil that had stopped the drive. The shaft also had to be large enough for disassembly. Bertha's damaged front-end components were enormous, and the repair required more than a mechanic crawling in with a wrench. Crews needed room to remove major parts, lift them vertically through the shaft, service or replace them, and lower repaired components back into position. That access pit became the centerpiece of the entire recovery. It was not just a way to look at the problem, it was a temporary underground worksite built in one of the hardest possible places, created so engineers could perform open-heart surgery on the world's biggest tunnelling machine. At the bottom of the shaft, Bertha stopped being a buried machine and became a dismantling job. The first target was the cutterhead, the enormous rotating steel face that had once chewed through Seattle's soil. It was too large to simply pull out as one casual piece of equipment. Crews had to detach it from the front of the machine, rig it to heavy lifting gear, and raise it through the access shaft with almost no margin for error. The cutterhead weighed hundreds of tons. Moving it meant coordinating engineers, crane operators, ironworkers, surveyors, and safety teams around a load large enough to crush the worksite if anything shifted. Every lift had to clear the shaft walls, avoid damaging the machine, and land in a position where crews could inspect it. Once the cutterhead was out, the real damage was finally within reach. Behind it were the main bearing and seal systems, the parts that allowed Bertha's face to rotate while keeping soil, water, and pressure from invading the machine. These were not accessory parts. The main bearing was one of the most important components on the entire tunnel boring machine. If it could not turn reliably, Bertha could not tunnel. And the repair was far beyond replacing a broken gasket. Crews had to remove massive components from the front end, inspect them, clean them, refurbish what could be saved, and replace what could not. The seal system needed major work. The bearing assembly had to be examined for damage and contamination. Steel surfaces, housings, bolts, and interfaces all had to meet tight tolerances before anything could go back together. The hard part was that this precision work was happening inside a temporary underground construction chamber, not a factory. Parts had to travel up and down the shaft. Tools and replacement components had to arrive in the correct order. Workers had to assemble pieces weighing many tons in cramped conditions, while the rest of Bertha remained trapped in the ground behind them. Even reinstalling the repaired components was a major operation. The rebuilt parts had to line up with the machine's structure, seal correctly, and reconnect to systems that had been idle for months. A slight misalignment in a machine this large could become a serious failure once the cutterhead began turning under load. By the time the front end was reassembled, nearly 2 years had passed since Bertha had stopped. On paper, the rescue had worked. The cutterhead was back on. The bearing and seals had been repaired. The access shaft had done its job. But nobody could prove the machine was truly saved while it was still sitting still. The only real test was waiting underground. Bertha had to start turning again, push forward, and show whether the giant could survive the rest of the tunnel. On December 22nd, 2015, after roughly 2 years of repair work, Bertha moved again. The restart was not treated like a victory lap, it was treated like a test flight after a crash. Crews brought the machine forward carefully, watching for signs that the repaired bearing and seals were holding under real pressure. Every vibration mattered. Every temperature reading mattered. Every foot of progress had to prove that the rebuilt front end could survive contact with soil, groundwater, and the weight of the city above it. Bertha was still about 1,000 feet underground, and it still had miles of tunnel left to bore. The machine that had failed was the same machine now being asked to finish the job. A repaired bearing could look right during assembly, but tunneling would expose every weakness. If heat built up again, if the seals leaked, or if the cutterhead resisted rotation, the project could slide back toward another shutdown. So the early movement was slow, deliberate, and closely watched. Engineers checked machine data constantly, crews monitored the ground surface. The project team had to balance two pressures at once, move fast enough to recover a schedule already damaged by years of delay, but not so fast that they missed the warning signs of another failure. And the restart did not mean the risks disappeared. In 2016, tunneling was interrupted again after a sinkhole opened near the machine's route. It was a reminder that Bertha was not operating in empty ground. It was passing beneath streets, utilities, waterfront structures, and a city that could not simply be cleared out of the way. Later, concerns about possible damage around Elliott Bay Piers added another layer of scrutiny, because the tunnel was moving through an area where ground movement could have consequences above. These interruptions did not mean the repair had failed. They meant the project was still alive in the most stressful sense, moving, monitored, and vulnerable. Bertha had escaped the access shaft, but it had not yet escaped the story. The real proof would not come from the first few feet after restart. It would come only if the machine could keep boring, pass beneath Seattle, and reach the end of the tunnel under its own power. On April 4th, 2017, Bertha reached the wall of the disassembly vault. At the north end of the route, crews had built a receiving chamber where the machine would finish its work. Behind that wall was open space, equipment, and workers waiting for the cutterhead that had once seemed impossible to rescue. Bertha pushed forward, the circular face grinding through the last section of concrete and soil until the cutterhead finally broke into view. For the project, it was the image everyone had been waiting years to see. The machine that had stopped after only about 1,000 feet of tunnelling had now completed the excavation of the tunnel. It had passed beneath downtown Seattle, under streets and utilities, and arrived at the endpoint under its own power. The breakthrough did not erase the delays, the lawsuits, the repair shaft, or the years of uncertainty, but it changed the ending of the machine's story. Bertha was no longer the giant trapped beneath the city. It had become the machine that broke, was rebuilt underground, and still finished the dig. After the breakthrough, Bertha's job was over. Crews began the process of dismantling it inside the disassembly vault. The cutterhead, shield, motors, and internal systems were taken apart in sections, lifted out, and removed. Much of the machine was eventually scrapped, a strange end for what had once been the largest tunnel boring machine in the world, but the tunnel itself was still not ready for traffic. Excavation had only created the empty underground passage. Crews still had to build the road deck, ventilation systems, safety passages, lighting, drainage, fire protection, and all the systems needed to turn a bored tube into a working highway. That final stage took nearly 2 more years. The old waterfront viaduct was closed, the new route was prepared, and drivers were shifted into a tunnel that had been one of the most difficult infrastructure projects in the country. On February 4, 2019, the finished 1.7-mile tunnel opened to traffic. Bertha did not live to see that day as a machine, but the path it carved under Seattle became the roadway, and the broken giant that once halted the project had carried the dig all the way to the end. Bertha's story became more than a delay on a highway project. It showed what mega-project engineering really demands when a record-scale machine fails in a place humans were never meant to work. The tunnel was finished because crews found a way to reach the unreachable, lift out the damaged heart of the machine, rebuild it, and send it forward again. If you want more stories about the machines and recoveries behind modern infrastructure, subscribe to Industrial Empire. Thanks for watching, and write a comment telling us whether you would trust a machine like Bertha under your city. Today, Seattle traffic moves through a tunnel that once depended on rescuing a broken giant underground.